Hello everyone. We'll just wait for a few more minutes and then start. In the meantime, you guys have any questions, then you can ask me. Okay, I think we can start. So I'll just summarize some of the things from last class. We saw about lambda expressions. And before getting into lambda expressions, first of all, we see a function remainder, right? It takes the integer n and then it returns n percentage m. So essentially, it does a modulo operation where it returns the remainder. Now, the idea is that the m value is fixed here. I could actually put it as a const true or not. It really doesn't matter. Um, the idea is that the divisor here is known and we want to um, have some input and then give some so that it returns the remainder. Simply, a very simple way of doing this will be something like this, where the m is known for the function itself, and the function is then called with for some input. Now the same thing, sort of the similar idea we want to get in through. This is the motivation towards the lambda expression, uh, where we have input a parameter which is taken as arguments and some values which are known to the function itself. So we can have a struct itself, which behaves like a class where the value m is known, and so here m is the internal variable. So the remainder during construction itself will have the value for m stored, right? Here it was 10. So similar to um, the previous case, when we call the struct with the remainder name and make some sort of an object, okay, rem, we pass the value 10 itself, so that the 10 is now a member of this struct. Okay, it's a private member. And now when I call the object with the bracket operator again, so sort of like a function, here it was the remainder function itself. The object now becomes a function because the operator, okay, with small parenthesis has been defined to take integer n and return the modulo with m as the remainder. Okay. Now, similar function, like similar um, functionality in the sense, whatever this code does, essentially the same thing is what we get even here using struct. Okay. So by dividing by 10, once the object is constructed, the value for 10 is fixed. And whenever we want to get a remainder, we just call the parenthesis like a function and just pass the value, right? Similar to that, we actually go to what C++ will do. So this was like the structure from C style, C programming paradigm. Let's look at the way a C++ will do the same. Okay, so there we get something called functors. So the functors are essentially um, like class, okay, class where the objects themselves behave like functions. Something similar to what we get here, where the object is passed a value and then we use this small parenthesis. So this uh, piece of code essentially looks like a function. Very similar to that, we have functors where the func, right, is an object of this functor class, and this functor now uh, takes values very similar to a function. How do we define this or construct this? Uh, Quite similar to the previous case, we have a public like operator n, right, which we have defined the bracket operator here. It takes the value 5, let's say. I haven't put any constructor, but essentially one can do the same for the remainder expression also. But so what here I'm essentially doing is there is a bracket operator. So whenever after getting func is getting created, so here there is no we haven't defined any constructor, so it will use a default constructor. So after then it creates this object itself. But since we're interested in just using it as like a function, so hence this piece of code where uh, the parentheses, like the small brackets, these are defined to take integer capital N, sorry, and return +5, let's say. Sorry for that. So that is the overloaded, not the overloaded. This is the defined bracket operator for this func, right? And then I can define another function inside this functor, which will be very similar to, because at end of the day, still this is a class and it can have member functions. So which takes n and then just does +1. So func can still access its member functions with dot by using the dot operator. So then dot you access that by as you do for any object. So for the object, then dot, then the function, and then pass the value. It's similar to this. Uh, Key thing to remember here is still the function itself, the object itself is like a still an object, right? It has all its properties. So it has private members, it has public members, like variables or functions and so on. Extra thing is that it can act like a functor also. Okay, that's the uh, extra thing you get by defining the operator, this operators in this way. Okay. Now, looking at another example, now we move to actual lambda expressions. So all these three examples that we saw, and whatever uh, code we, whatever, how do I put it? Whatever functionality we want from all these three sort of code, and we can see that these are essentially doing the same thing, but in different ways. C++ actually has lambda expressions to do exactly this. So, okay, recapping. So lambda has three, okay, well, four parts where there is a capture list. Okay, so these are the values that the lambda expression knows. Okay, as in has access to those values. Then it has parameter list, which takes as parameters. Then there will be a return type, or depending on the body, it can even infer the type of the return. So sometimes it's actually like optional. And then there is a body. Okay. So here I take an example where this is a completely lambda expression with the function call. Maybe I'll just put it this way. Okay. So I'm defining a function print, okay, such that there is a capture which doesn't take anything, which is also okay. There's no input to the parameters also, parameter list. And then there's no return type. That's also okay, because from the return, the body of the statement, it will infer it's a void type actually. So because it's just a print statement. Now this curly braces will tell the portion of the code, which is the body, right? So it's simply a hello world program where it prints the hello world characters. That's it. Now, that is the how we are defining a print function, functor. I mean, a lambda expression actually. So to use this, you just have to call that function and then put the arguments and within this small brackets, right? Since it doesn't require any inputs, you can just leave it empty, and the as many times as you call, it will just call this um, print function. Now, this is the way I define it and then call it. One can actually also just do this way, where let's put it here, yeah, where you define the lambda expression very similar to here. So give the capture, give the parameter list, give the body, and then finally just add this small brackets, so that the function that you defined, you are again just uh, calling it. So I understand it's since why do I just consider and use it then? Sometimes you don't want to like define a new name for that function, just have a body or something, just to use it. So this is a syntax. It should be. I'm mentioning this because it's just a syntax. It should be familiar with. That's all. Depending on use cases, you change which way you want to write your lambda expression and all. Okay. So far, so good. Okay, so next we take another example where so I have a main, right? So here I have a lambda expression inside an if clause. I hope you can see the if clause. So this is the if clause, right? And inside that I have a lambda expression. Okay. Now the lambda expression has a return of, if you see the body, so this is the body of the lambda expression. There's a return with equal to equal to. So the return type is a Boolean. It's either true or false. And that's exactly what if statement expects. Okay. So what we are doing is here is having just no capture. Essentially here it's not required even. Then we are saying that we'll have a parameter list with two integers a and b, right? And if you see here, within the brackets, they're actually passing it itself. So it's just another way of looking at lambda expression. You can put it inside a name and then call it later. That's what we did here. But this is one way of looking at lambda expression. They're passing two values, 8 and 8, right? And then it's printing true statement, which it will here in this case. Else it will print false. Okay. One can even define a lambda expression like to some give it a name actually. So essentially it also behaves like a functor. Yeah. So name of the function, what you are defining, and giving it some parameters, and that's it. So very similar to the syntax. So you have capture list. Similar here. No, like there's no uh, input to the capture list, but then again, it's just empty. It's not required also here. And then there are two inputs, A and B, integers, and there is a return body. So we define it as a clause, and then pass it different arguments, and then print statements, and then print the bot like different things. Okay. Now there is a 8, 8 we're passing was just in one example, and this should print true. This is the expectation. And then after that we have 8, 9, which should print uh, false, right? Okay, maybe I can just quickly show the answers. That should be good. Okay. Okay, remainder is 5. What we expect. 10 is the base, 15 is the input, so remainder is 5. In this case also the same code but with structs. So maybe okay, great. Same answer. Then with lambda 3, 5. Okay. So functor prints 10 because it's 5 plus 5, 10, and 18 plus 1 is 19. Okay. Uh, yeah, then the in the lambda expression, where if you see the print function itself prints hello world 5 times, which is what I see here. There are the hello world is printed 5 times. Then just the empty, not empty, I would say the single lambda expression here, which is just once called, it prints hello world 1. Okay. Right. And then if we just print this example that we just saw. So the first is a true statement because 8 is 8. Second is also true because again 8 is 8, but maybe I'll just give 9 and 9. Okay, it should be true. Then we call a clause function with 8 and 9. So since 8 is not equal to 9, it's a false statement. Okay. Now we look at another example where we are doing essentially the same three things that we saw before, uh, using just function, using structs, using functor. Now we are using lambda expressions to do the same thing. Okay. The M is defined to be 10, and then uh, yeah, yeah. So M is defined to be 10, and then we define the remainder function, okay, the lambda expression. Uh, we say that it captures the value M, okay. So since here it is defined to be 10, so we want it to capture the value 10 itself here. And then capital N is all the parameters that it will take multiple times. Essentially what this does, or even this does. Okay. So now the body of the function, what we're defining to be is return n modulo with m. So that gives us the remainder. And n is known because it's the input to this function, like the lambda expression. M is known because it captures it. Okay. So this M, because we're passing it, we want it to be known and defined. Okay. So let's see the output for this. The remainder is 5 as expected. So same input, what we're giving to all the previous files, 15. And when divided by 10, the remainder is 5. Okay. Then another example, taking another example. So yeah. We define a temp equal to 0, right? And then define the lambda expression sum, okay, which captures temp by reference. Now, this is important. Here it captures by value, okay, just and right, but here it captures by reference. So the way you pass the capture list by either by value or by reference changes how your body will behave. Okay, so for example, like taking this example, we capture temp by reference, then define the body temp plus equal to 9, where n is the input argument, integer n, right? Now, this is the function that lambda expression that we defined, sum. So sum, when we pass 15, right? So we should expect what to be the output. So we're trying to put print temp, right? So 15 is what we are giving an input. Temp is already known to be 0. So any guesses? What will this first line sum print? Okay, it will print 15. Okay. And then again, I'm passing the same argument and printing the value 10. Okay. So what do you expect will happen? So slightly different than before. If it would have captured by value, it would have fixed temp to be 0 always. Okay. But since it's a reference, the value when we change temp here, it's just it also gets it also affects the original value here. Okay. So let's print and see. Yeah. So that's what I was talking about. So we have 15 already in this line. Like that's okay. It prints it. I mean, that also happens because it is actually changing this reference. It's taken a temp as a reference. So this temp itself gets changed. So when we print temp after calling sum 15, 15 has already been added, and that change reflects here. Again, when we call sum as 15, that change reflects here. Okay, and so on. So hence we see 15, 30, 45, and 60. Okay. Now, taking another example where let me define something called a val equals to 0. I'll define a variable val and another variable ref. Okay. Now, for lambda expressions, if something is being passed by value, like something like this, ideally you should actually initialize it. Otherwise, if you don't initialize it, let's say it holds some very large garbage value, it will just capture that itself. Okay. So it's good to initialize those. And references are okay because anyway they get modified or printed or whatever. But anyway, it's going to modify it inside the body or something. So you actually don't need to initialize it. That's all. But essentially, the key takeaway here is that the capture list can be through a pass by value, which is which val does here, or it could be a pass by like a capture by reference, right? Which ref does here. Now reference will keep changing, but val or this variable val gives the value that it first captured for the lambda expression check. Okay, and then this is defined to have two taking two parameters as inputs. Okay, then the body itself is just a print statement where standard cout is just val ref params 1 and 2 what is what we're printing. Now what we'll do is change ref to 4, okay, and then pass parameters 10 and 11. So changing it to 4 should actually affect the value that we see for ref. But what do you guys think will happen for the value val? Let's print and see. So I mean, it actually prints all the answers, but it's okay. Uh, so ref here, when we print with 4, right? So that actually just prints. So if you see the first line, it prints 4. What we expect, even if it captures ref previously, it is capturing it by a reference. So when you change this variable ref later, right? It again, it knows the new value. So when we call the lambda expression check, it actually prints the new value of ref. But it will print the value of val, which is 0, which it has captured initially. So hence it prints 0 here. And parameters 1 and parameter 2 are passed as 10 and 11. So those are printed as 10 and 11. If we go to the second part of this code, so I'm changing it val by 5, right? And then calling the function again. So this time you see that the value still doesn't change because during the capture, the val variable was captured the value, the check expression captured the value of val to be 0. So because it's a pass by value, it doesn't matter if you change val variable later on, right? So that's essentially the difference here. So if you print the value again, it prints the exact same thing because here we just try to change val which doesn't uh, affect check uh, lambda expression. Again, if you print like change reference to 17 and then pass different values, that gets changed. Okay, val still remains to be 0. Okay, hope this example is clear. Okay, we can do the same very similar thing with a struct also. So we use lambda expressions, but the idea is that it is maybe I just put it here. Yeah. So if you compare, essentially what lambda expression does here is what we are implementing in a struct, but it's just less lines of code and much cleaner way of writing the same thing. So we define some integer val as 0, integer ref. So essentially the same portion of the code. Now this struct is defined as some internal variable of val equals store. So checkf is underscore f is something we are defining. So valf is also a member variable which will store the val what you're passing with a reference to ref also. Ref stores the reference to whatever it will pass. Ref will be passed here, which will be this only when we define it, right? Then a constructor of sorts where we pass val and ref, and then define val f to be val, ref f to be ref with no body required. Then we define the operator, this small brackets, where it takes two parameters, parameter 1, parameter 2, and then just prints the same body that we have in the lambda expression. Now, we'll define the object just auto is okay here. So because the struct is the data type of check, the object, because we're using check underscore f, right? This struct to define uh, the object check. It's okay. You can use auto to for not worrying about the data type and letting the compiler handle this. So check underscore f takes value val, which we defined here, right, as 0, and ref as a reference. Because it passes this val by value. Now val underscore f here internally for this object check, internally it is defined to be 0, and that's not going to change because it has been defined in the construction itself. But it has a reference to ref, right? And similarly, if we do the same exercise, changing ref equal to 4, 5, and 17, you will see it gives the exact same output. Okay, yeah. Where the value doesn't change, because once it has been defined, it's not going to change. Then we have references where 4, 4, 17, like for these examples, and when I change 17, it changes. Rest of them are parameters which whatever it takes. Okay, correct. So this is sort of like a summary of what we saw last week. Today we'll be discussing lambda expressions. Sorry, I meant smart pointers. So last week it was the lambda expressions. So today we will motivate towards smart pointers and why do we need them, right? So a brief about uh, why we require smart pointers, because generally in C or C++, managing memory becomes a little tricky. So while its high performance is quite a main feature that why is the reason why people gravitate towards C or C++. Uh, while forgetting to manage memory properly, like essentially because in C or C++, people use pointers a lot. Forgetting to allocating memory through and accessing them through these pointers and forgetting to delete them can cause a lot of issues, memory leaks, it's quite unsafe, and so on and so forth. So hence the idea of smart pointers came along. So we can take some examples as to why it was required. Okay, so okay, so I try to compile this. Yeah, that's fine. Anyway, there is no body, so that's fine. So as usual, I'll have. Okay, there's a question. Why do we put additional brackets after operator function in the last example? Oh, okay. Let me just put that. Okay, is it which? Can you tell me which uh, file you're referring to? Is it from lambda 1 to 9? Is it the line lambda 9? Okay. Can you point me to the line? So do you mean this line 13? Okay. So what we're actually doing here is forget this part of the code. Okay. So just focus on this first. So I have a struct checkf. Okay. And it has some internal variables. For simplicity, think of this struct as just a class. Okay. Imagine I just wrote a class where this is the name of the class. These are the private members. Okay. And this is the construct of that class. So it this portion is the input. Okay. And this is essentially the constructor when then it defines the internal variables and it's done. Okay. That's fine. Similar to a class, what we can do is have some other functions to that class. So here, this operator, okay, is essentially a function which defines that if I have an object, so this is just a different way of defining an object where I'm saying auto is essentially the struct here, but you can think of it like this is a class where check is the object of this class, check underscore f, and take some values. Okay. Now that this object has been defined, okay, I'll use a function of this object. Okay, which is this thing. Now, this is a different way of writing. It's not just a named operator. Okay. Here we explicitly use the word operator. Okay. So we actually spell it out. Then we use this parenthesis, right? The small brackets to define that when I call this object with these operators, ignore the inputs for now. So when I call this object with these operators, this function will get called. That's essentially what defining this operator means. Okay, it's not. It's also how do I put it? It's not something very commonly written, I guess, because people are used to just seeing functions like simple functions, like this. So where there's some data type, function name, and so on. But this is also a very valid function for that object. Okay. So similar to what we did here, like in functors, what is essentially what I'm doing here also, where I'm defining this function. Okay. So the function essentially is this operator, which expects now then this bracket encloses what the parameters are. So for my uh, check here, which is the object, I'll have this brackets. Okay. So those brackets are this function itself. Okay. They expect two inputs. Those are the 10 and 11. Okay. The essential idea is that like doing this and not just calling a function like what we did here. So func, then I use the dot to access this named function, right? So that's the difference. So I can use dot to access that function and then give some parameters. But if I define the bracket operator for the object itself, the object here is func, or in that other case is check. You can just call that object, use the brackets, and pass your parameters. Okay, very similar to that. What are we doing here? Pass two arguments. Again, call check, pass two arguments, and similar here. Okay, I hope this is clear. Still have any questions? I can repeat. Okay, awesome. Thank you. Yeah. So, okay, moving on. Let's look at some examples for the smart pointers. Right. I'll just close this. Okay. As usual, I'll include the header file because we'll be printing stuff. Then I'll define my main function it doesn't take any inputs with uh, with default return 0. Now, let's say I have some class, okay, which is my class, and I define an object of this obj. Okay, it's a class pointer actually, and I define it to be like I'll define a new class actually. So I'll call it, let's say, my class. Now, this is fine, but what happens at this first line is it creates the ownership, as in the object which is of type my class pointer. Essentially, it's a pointer of data type my class. New my class will, you can think of it like it's creating that new object. So now Yeah. Just give me a second. Yeah, sorry. Um, okay. So what we're doing is creating an object. Okay, with the new operator creates a object for whatever you want. So let's say I want to create an object for this my class, and I'm putting it as a my class pointer. Okay. So the important thing to note is the object here, it creates this line creates an ownership, and object pointer stores it. So this has the ownership now. Okay. Then let's say I do just this object equals to 0 or null or whatever. Okay. Now what this does is the object now loses uh, ownership. So it no longer owns the uh, ship. Yeah. It no longer owns the actual uh, memory to that object that was created, obj. Okay. Now, uh, but one important thing to note here is that still that allocation is exists. So for this my class, when we did new, the memory was created. Okay. And then uh, we're pointing the pointer to that to this object. Okay. If I set that to 0 or something, now this obj is just a pointer. It is, let's say it just points to null or 0 or something now. But still, the actual object which was created, nobody has ownership of that. So that's a memory leak. So this is an example where memory leaks can happen when you set some objects to some null or some other value, and then they lose ownership. The problem is that the actual object that was created still exists and nobody deleted it. Okay. So this is just a memory leak. Okay. I can't compile this because I still have to write my class and all, but I hope you can uh, see the example. Like imagine there is a my class. Essentially, it doesn't matter what the class is, but yeah, this example holds good if there is a class. Now, the other thing you can do is a copy. So this is just an assignment. I'll put memory leak in assignment, where I'm assigning a new my class, okay, to object. Then I'll have another example, okay, where I'll define my class. Like let's say it's pointer A as new my class. Okay. Again, this create ownership as this example. Okay. Next thing I'll do is I'll define another pointer, let's say B, to be A. So what I'm doing is like a copy. I defined an object like this new operator, this my class object of this custom data type my class from this class, and store the pointer to that object in A. Okay. Extra thing, the next what I'll do is B also make like define B as a my class pointer, and it will also store the same pointer to as A, as to the same object. Okay, so this is a copy. So now A and B, both of them are pointing to the same object. Okay, so here we are actually copying the ownership. Okay, next what we'll do is let's say I delete not A, but first delete B. Okay, now let's say I try to delete A. Okay, so now what happens is B was pointing to whatever object, so it deletes this object. So at the imagine, so remember, the object is just one thing. This whatever is created by this new, the this A is just points to that object. Okay, B also points to the same object. It's just pointers. Now, if I delete B, it deletes the object. Okay, and also loses ownership. Removes, actually, it's better what to say is not loses, it removes ownership, which is actually what one should do. Okay, so this is a behavior that is expected. Okay, so this removal of ownership happens when you delete a pointer. Now this is good, like this is what you want. But now for this example, the next line, when you try to delete A, already that object is deleted, right? So it will try to delete that pointer, but there is a object it is also pointing to, right? How will you delete that? So this is an error. Okay, so essentially here you can say it's a double deletion. Okay, so error with copy. So this was an assignment, like an assignment operator equal to, and as in this part actually, when you equal it to something else, and here it is error with a copy. I copy the pointer to some other variable like B or something, and then delete it. So if I've already deleted object which it is pointing to, I cannot delete it again. So this is essentially another error that you can encounter using pointers. Okay. I hope this example will motivate you why we need sort of a better management of pointers. Okay. So another example. So these are two examples where you can um, face this issue. So what one can do is like a solution to this. As just a this is something you can actually cook up. So I'll just write that. So let's say I have void um, function. Okay, this is some function I just write. Okay, then I'll have, let's say, my class, same class, but with pointer, let's say A equals to 0. Something I just defined. Okay, now I'll have a try and a catch where the try says my A will take new class. Okay, and let's say there is a function it is pointing to. Let's call this as function. Let's call that function. Okay. The other part of the catch is like the try. So you try this. If there is an error, you catch it. Okay. Delete the object A and throw some exception. This syntax for try and catch is quite useful, where you're trying to run some portion of the code, and if it throws an error, then you switch back to a different part of the code, do something else with it. So essentially, this is uh, good practice also. So to have try and catches where error can be then dealt with. Okay, so with this, and then let's say I do this, and then I can just delete it. So if this is successful, then I want to delete my A, and if the uh, catch, let's say what you're trying to do with it, it fails, you can just delete it and then throw an exception. Okay, so the code ends. This is a very basic way of handling these errors, but yeah, as we'll see now, I mean, and later on, there are better way of handling this same functionality. We call it smart bonus. Yeah. Okay. So then let's say I have two functions. Okay. So something like this, where this is B. Okay. I'll call for A, and then I'll also do the same for B. Now the thing is, it has to uh, do like if you have more and more pointers, okay, and you want to do some like access some member function or something, then you have to keep repeating this actually. See, you have to do the B throw and then again B. So there's a lot of repetition in the code. Okay. I hope you appreciate the this boilerplate code. While yes, you can have a code which deals with this kind of errors, but doing it for all the pointers just makes it quite large and cumbersome to see. Okay. So because of this, we move to smart pointers. Okay. The uh, okay. So the essential idea behind smart pointers is that it supports some idioms. So for example, the first idiom is RAI, which means resource acquisition is initialization. Init initialization of what is this? So we have seen in previous examples where let's say I'm trying to construct like create a new object. So its constructor gets called. So that is we'll use that idea where let's say my smart pointer captures a new object creation, then it will initialize it. Okay. Similarly, when resource gets released, it will I'll destroy it. Okay. So this is RRID. Resource is destruction. Okay. Now the idea is that we're essentially taking advantage of acquisition and release of resources to initialize and destroy them, like free the memory. You can think of it like going out of scope, or that will be like a resource release, or like, or you're trying to create the object itself, then I'll initialize the object, so on. We'll see some example for that. So okay, I'll maybe write this. So let's say this is a uh, you can think of it like an implementation for this smart pointers, while the smart pointers themselves exist in the standard library, one can also implement them this way. That's what I'm writing now. But you need not write this whole thing again and again, and just directly use the uh, already available standard library smart pointers. I'll also show the example of that. So, but this one is just for understanding how one can write some kind of or define some kind of smart pointer. Okay. So I'll define public. Okay. Um, some sort of a constructor, right? Smart pointer, which takes so it's a templatized class. The name of the class is smart pointer, but it's a templatized class with class T. Okay. It takes a pointer of type T pointer, like the type is T, capital D, point T, then whatever it is acquiring, right? So this is the RAII step. Resource acquisition is initialization. Then in itself, it will have some sort of a member, let's say pointing. And it will define this pointer to that. Okay. So this is the construction. Now I can have sort of a other functions for this. So let's say the alignment operator. So it will look something like smart pointer. Then we are like a password reference. Yes. So operator equal to I can define many operators. I'll define the equal to operator with const smart pointer reference like something else. I can have destructor for this. So we see the constructor here. Destructor something like this. So smart pointer and that's it with the pointing to delete. Delete what? Delete this guy. Okay. So this step is the RRID. So I can actually just keep writing some more things like oh, sorry. Maybe define the private. Hmm, this one. Just define it here. It is of data type T star. So it holds that pointer. I maybe I'll just give another example where like add some more to it so that it looks more useful. So this is my function. Okay, so like void function. Actually, it's not really required. Okay, yeah. So this is sort of a boilerplate code for this is input. Yeah. So this is sort of a boilerplate code for like I'm writing a class of a smart pointer. So essentially what it does is I can have any kind of pointer, a double pointer, a custom defined another class or with some pointer object like what we saw here, like my class pointer or whatever, right? My class star object, my class A, my class B, any of these. So what smart pointer will do is will pass that smart pointer to this object of the smart pointer, right? So it acquires that, and as soon as it acquires, RRI happens. So acquisition is initialization, okay, and then as soon as the object of smart pointer gets deleted, the pointer gets deleted. So automatically the uh, management of resources by some pointing, okay, is managed by the object of smart pointers. Simple as that. So essentially, I'll repeat. I have an object or pointer or some resource I defined. Okay, this actually could be anything. What we'll do is we'll wrap this object with a smart pointer class so that when the object gets created, the pointers allocation happens. Okay. And then when the object of smart pointer gets out of scope, the pointer it is holding automatically gets deleted. Okay. So it will look something like this. So I'll write the body of the main function, the main. Yeah. It will look something like this. Smart pointer. So remember, this is a templatized class. So I have to pass some kind of template. So here now I'll pass my class. Imagine that is defined. So essentially this my class is what I have been using here. So I'll pass the data type of my class. Okay. The class name actually. Then I'll make smart pointer, say this is SP, smart pointer, takes new my class. Okay. So here RAI happens where the new my class object, when it gets created, SP, which is an object of smart pointer, holds this pointer to my class. So the new my class, okay, whatever pointer it is returning, that is captured by this pointy. Okay, that is that pointy here itself. Now that gets stored inside pointy underscore. The pointy underscore is essentially that pointer to my class now, which is held by smart pointers. Okay, great. Now, if I want to call some function, let's say I define, no, sorry. Okay, maybe I'll put that function code so that mm, yeah. So uh, I'll write this operator too so that uh, becomes easier to see. And, this arrow operator I'll define const, and there'll be like let's say a lot of lines in the code, and then it has a return pointing. Okay, thank you. Very similar to that. I can have like a reference. Sorry for that. Reference for it, but this time it will be this star pointer, and again return the dereference to that. What I'm trying to say here is, let's say I want to call some function, okay, of SP. So SP is the object of smart pointer. So SP, I'll call. Let's say there is some function I have defined. So now what this will do is this will sorry. Yeah, what this will do is this will actually call SP no, operator. Okay, and that whole thing is called the function. This function is function of defined at for the my class operator. What I was trying to, let's say, define it and try to access. So this function is defined for my class. So my class is a class, A and B are objects. So I'm to access a member function of my class function. Okay. So I can just do this A arrow because it's a pointer. So I use arrow operator and function. Okay. Now let's say I want to do the same thing, but from smart pointers. So smart pointer, I can access now because it has acquired this uh, class, like object of this class, right? Then this SP function will to you use the same function. I can just copy. I can just use the arrow operator. Okay. Now, essentially, what it will do is the function will call the function of the pointer it is holding. So what we're essentially doing here is this bracket operator. So because of this bracket operator, we can return the pointy and then ask it to just give that return that function itself from the, because SP, which is this class, smart pointer class, it has access to this pointer, right? So from here itself, we can access its member functions internally. Essentially, this is sort of the idea I'm going for smart pointers. And there are much, I mean, you don't have to write all this custom classes to use smart pointers. As I mentioned before, it's available inside C++, but it's good to look at how the smart pointers will be implemented if at all you want to write your own smart pointer. Yeah, okay. Um, right, let's look at some examples. Or that's fine. Okay, so first of all, we'll look at unique pointers. And just a small note, you can't compile and run these programs. It's just an example I'm writing. You still have to write some basic my class to for it to even compile. Runtime, you actually have to do more, write more code, but I hope the idea is clear here. Okay. Pointers. So let's take example with unique pointers. Okay. So the idea behind unique pointers is that um, it we define a pointer, okay, a single um, okay, let me put it this way. After resources allocated, we can have a pointer accessing that value. Okay. Now, either we always want a single pointer to have access. Let's say I can have multiple pointers pointing to that, but let's say I just want a single pointer to have access to that, or have ownership to that object. That's what unipointer does. It or so when essentially what happens is when your unique pointer gets out of scope, the object gets deleted. Okay, whatever it is pointing to. So let's look at some example then for this. So essentially that is the idea about unique pointers. So the summary is that the unique pointer points to an object, right? But uh, pointing at a given time, only a single pointer will have resource like manage that resource or the object. Okay, so let's do it this way. Yeah, okay, let's write some stuff here. Let's say it is then sort of like a class, right? Constructor and destructor. Okay. Body is standard out. Let's say I just want to print food because during its creation, it will just print this. I'll put a new line, that's fine. After that, so this is the constructor. So I'll just copy this. The destructor, I'll just put it like this. So I know that the destructor was called. Okay. Then I'll have uh, function bar. Okay. and then define the body. Something like this, where we are just saying it is inside foo names, sorry, foo name as the bar. Okay, and that's it. Now, another function f, okay, is just defined. What it takes is a const reference to foo, actually, this whatever structure we defined. Const reference, and the body we can put it something like this. Okay. Now, yeah, onto the main function. So now here's the thing. We'll make a unique object. So this is a struct, right? Or you can think of it as a class or something. Now, what we'll do is make a pointer to this, but through unique pointers. So let's see that. Standard. Oh yeah, actually this will be required. Include memory. Okay. Now, yeah, unique pointer. It's templatized, so you have to pass the name of the class or struct or whatever you want to make a pointer out of. So who is the class? Then define a pointer p, okay, equals to standard make, not make shared, make unique. Yes, make unique. Make shared also exists, which we'll look at next. So this example is just for the unique pointers. Okay. So I'll pass the uh, template for the template, the class name itself. Okay, and then make unique function. That's it. Okay. So this syntax for standard unique, like standard unique pointer and make unique, are from C++ 14. Okay. And now the extra comment here is that we now owns an object of foo. Okay. The other way of writing the same thing, I'll just make a comment here. You can write it like this also. Unique pointer to p equals to sorry, no equal to. You can just pass it with a bracket and then do something like this. Okay. Very similar to what we saw about this. Yeah, very similar to what we saw here also. So like just pass new to new of that class. So whatever pointer will get created, it goes to the constructor. Very similar to that. We just give it a for the p construct, the object p. So constructor of standard unique pointer will just take this foo and then create a smart pointer. Okay. More specifically, the unique pointer in this case. So this is from C++ 11. Yeah. Same thing happens. P owns. Uh, yeah, you can choose to write it this way. Anyway, it knows that it's making a unique pointer, or you can actually specifically mention that you're trying to make a unique pointer out of. Okay, you can even do that. Yes. Now you can put like some kind of a if now. So if p, well, let's say this p pointer is not just a second. Yeah, let's say this p pointer is not null, so then it will execute this next line. So I'll access the bar uh, function inside this foo class. So bar, that's it. Okay. Then some other lines of code. whatever we can write. Okay. Now this part is important because I'm keeping it inside a scope. So that will actually come into play now. So I'll make another standard unique. Okay. Pointer plus foo. Okay. Then this time I'll call it q, let's say. But I'll have another uh, function called standard move, which I'll pass p to it. What this will essentially do is, I'll make a comment here itself. Now q owns foo. So in this line, what I essentially did is I made a new object of like for foo, and a smart pointer p is now pointing to that object. Okay. With standard move, now q owns that object. Okay. Thing about unique pointers is only one pointer, either q or p, can uh, have ownership to any object. Okay. So using standard move, now q doesn't own, sorry, p doesn't own, q owns the object. Okay. The next line one can do is call something like this pointer. Keep remember this function which takes cross reference to foo, right? So we can just call f and pass pointer q, okay, dereference q, and then pass the object of that, okay, as a reference of foo. You cannot do the same with p. I mean, as in data type wise, it is fine, but it makes sense to pass q, right? Because q is the one which is owning the object foo. Okay, not p anymore. Then another thing we can just do is, because only one can have ownership, you can again transfer the ownership back to p by doing something like this. So standard move. Then just put inside bracket q. Yeah. So we move q to p again back. Here we created q by moving p to it. Here we again move q, the object owned by q, to p. Okay. Then yeah. Now here's the nice thing about smart pointers. Because the object is owned by p now, and anyway, q will go out of scope at this, it will automatically get destroyed. Now, if it was p, let's say q, we didn't have this line where q was owning the object, right? Then once it goes out of scope, the actual object gets destroyed. Okay, but I'll just write this destroying q. Okay. After this, I can still again write, let's say p. Yes, q doesn't have any scope here, so that's 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 there. And again call the bar. It will work because I moved the resource to back to p again. Okay. Now for this line where the main function ends, very similar to what we saw here. Since q gets destroyed, here p goes out of scope. Okay. So, yeah. So this p that we defined inside main is inside these curly braces. So here p goes out of scope. So foo instance is destroyed. P, we write it here. P out of scope. Okay, great. Yeah. Yeah, that's it. So this is essentially what unique pointer looks like. There's another very useful smart pointer called shared pointers. Okay, standard shared pointers, where the idea is that the resource is now managed by many other pointers. Okay, but the nice thing is because they are shared pointers, okay, the usefulness comes in the sense that once all the shared pointers get destroyed, the object gets deallocated. Okay, so the standard itself defines shared pointers such that once all the shared pointers get destroyed, okay, the the object itself also gets destroyed. Okay, we can take another example. Okay, very similar to this. Um, the memory headers. So let's see the integer main. Okay, return 0. Okay, now here I'll make a standard shared pointer. Okay, let's say I'll just make it with integers, right? Call it p equal to. We'll use the C++ 14 way of defining it. So sorry, make shared. So make shared. Yes, integer and nothing. Okay, so this makes a integer pointer which can be shared by many other pointers. Let me define for dereference p to be let's say 3. Now I will print this one, and again this is I think obvious what it will do. So dereference p. Okay, so I hope the output of this program is clear. Okay, this one let's print and see. This 4. Yeah, phase 3. I think the code is pretty straightforward in this part. So essentially, we'll define the shared pointer p. Okay, uh, make it store the value 3 and then just print it. That's fine. One extra thing what we can do is there is a useful function with shared pointers where you can keep a count of them, as in how many how to put it, how many shared pointers are pointing the same object. Okay, so shared pointer class itself keeps count of that. Let's try to use that function now. So standard cout. Oh, sorry. Okay. P is a resource counter RC to be this with, then we'll use this function called p dot use underscore count. Yeah, so okay, of course I print this. Okay, let's print this and see what output we get. As expected, we should get resource counter as 1 because currently uh, whatever integer it is pointing to, only p is the only pointer which is pointing that resource, which is value 3, sure, but only p is pointing to that. Okay, so hence when we print the resource counter, it is 1. Okay, let's say I make another pointer, shared pointer, okay, which should take again integer. I just want to make the same pointer again, like same pointer to this. Let me call it q and pass p to it. Okay, now the second pointer q, which I just defined, it will point to the same object. Let's say I print the resource counter to P. Okay, but I'll use Q this time. Okay, and P here this time. We'll call this as Q. Okay. This is maybe number is this counter or one dot. Yes, this will belong to the second line of codes. Okay. Yeah. So the first line that is okay. So P resource counter is one. That is fine. Because only P is the one which is pointing to 3, right? In the second case, I have two pointers now pointing to the same location, right? So it is Q and P. So the resource counter, okay, if you use for Q and P, both of them point to be 2. Because now resource count, if you think about it, both of them are pointing to the same object. So this how many number of pointers are pointing to the same object is known by all the pointers, all the shared pointers. Okay, that is what this use count keeps track of. So if you go through Q to count it or P, you'll get the same answers. Okay. Right. There are various functions also you can use. So you can even let's say P dot reset. So what this will do is it resets the shared pointer. So essentially what happens is this P pointer, which was pointing to the value 3, wherever that memory was, it will not no longer point to it. So the only thing that will point is the pointer Q. Now, neither of them have gone out of scope, so that resource is still very much allocated and very much alive. But once it goes out of scope here, both of them will get destroyed. Okay. P, while it did not point to anything, it's still just a simple pointer. It also get destroyed. Okay. The other thing you can do is, yeah, do something like this. Reset it, give it a new pointer and store the value 11. So it will have a new integer pointer. Okay. Because P has has been defined to store integer shared pointers. So it will store the value 11 in some like allocate memory, store the value 11 there, and then point to that location. Okay. This is another way you can use like redefine some shared pointers. And again, if one tries to print the resource counter here, okay, what do you guys think will happen? What would it do? It points one because we have reset the actually this line is also not required, but I hope we can get that. This line itself, what it will do is P will no longer point to the integer, no longer point to just 3, right? It will now point to something which is storing 11. It's a different memory location. So the resource counter here returns 1 because only one pointer, which is P now, is pointing to this memory location which is storing 11. Okay. Similarly, you can just assign null pointers also. P is null PTR pointer or something. And then if you try to put resource counter, it will be any guesses what will happen? It is 0 because P is not pointing to anything anymore. I'll make it 4. Yeah. Okay, so that is 0. Nice. Next. These are more or less the two very important smart pointers that anybody will encounter. Uh, First one is the make unique, as in the unique pointer, where the idea is that for a given resource, like some memory, we usually access them by using some pointers, right? Only at a given time, only a single pointer will have ownership to it. That's what unique pointer does. As soon as that pointer gets out of scope, okay, the resource gets deleted. So for in this example, P is my unique pointer. Okay, it is storing some memory to the foo class. Okay, as soon as the main function gets called off, P and subsequently the memory that is it stores for the foo class, like that object, that also gets destroyed. In this example, the main difference is that shared pointers will have, like, you can have multiple pointers which will be, let's say, the those are shared pointers. Those will point to the same object, and you can have reference counters to keep track of them. And when all the uh, shared pointers pointing to some resource get out of scope, okay, that resource gets automatically deallocated or destroyed. Okay, there is one more smart pointer called weak pointers. Sure. Fine. Okay, so while there is a difference definitely between unique pointers and smart pointers, but they have one common thing, that both of them actually own that object, right? So shared pointers can modify that object, and actually all of them have ownership. Unique pointers also have the ownership, but sometimes you just want a temporary ownership to some object. So that's when you use weak pointers. So yeah, this should be include the memory. Weak pointers, right? Uh, let's call this as W itself, right? WP. I'll define a function F, okay, then have a condition if, don't worry about the data type, is let's say there is a pointer, okay, yes, 18. For that weak pointer, I'll have a lock. So you can actually just put a lock so that the shared pointer uh, gives ownership to this. So then you'll have standard cout, let's say. Just dereference this pointer, shared pointer. Okay, this is some shared pointer. Okay. From that, we'll have a temp. So we'll make sure that weak pointer has a temporary ownership and does some work with it. Okay. That's the, yeah, there's the if part and the else part. Standard cout. The WP is deleted. Else, if you can't uh, access it, right? So weak pointer essentially means the idea is that if my resource actually exists, then I'll do some work, or I just throw error. That's it. It's in a way, because it did not have ownership to some object, right? So when it acquires tries to acquire an ownership, you can have the functionality to check if it is able to acquire it or not. Then, sorry. I'll have auto. I'll make a shared pointer. Okay. Standard make shared integer and get some integers there. Now the weak pointer will, I'll say the shared pointer SP. I'll assign it to the weak pointer. Okay. Next, I'll call the function f. So function f will call this, right? And it will check if we there's a lock on the weak pointer. It will then print uh, a shared pointer, or it just says it's deleted. Okay. Then after that, yeah, this is one way. But if I put it inside the scope, right? So now here this shared pointer also gets deleted. Like if you see it goes out of scope. So the resource doesn't exist. So if I try to call f now, here it will print the else part. So it prints the if part, sorry, it prints the if part here, it prints the else part here. Okay. That's it. Okay. Okay. Yeah. So these are some of the things that I wanted to cover today. So essentially, what we want to do here is I'll maybe summarize this part. We want to use smart pointers where they are based on two principles: RAI, RRID. With RAI as resource acquisition is initialization. What where what happens is, let's take yeah, this example. When you make unique pointers, so when it acquires the resource, right? Make unique or with new or whatever. P will initialize making the will call the constructor of the class foo and creates all the objects. So it calls the constructor, it will print foo and all that, right? So that is the idea behind RAI, where when you acquire resource, right? So you acquire resource now, like with new or make unique. There you start doing the initialization or calling the constructor and whatever functions associated with it. Okay, or whatever the body says. You can have like I did not put, okay, it is in the other part. You can ask yeah, this one actually. So you can have a constructor which takes some arguments. You can set all the private members and have a body also, like something like this here. Okay, so this is the RAII part, and the next part is the RRID, where resource release is destruction. So in this example, where P goes out of scope here at this point, right? P goes out of scope, then the destructor of foo is called, which is this one, and then it will print or it will do whatever the body of the destructor does, like whatever we have defined. Okay, so the fact that objects themselves go out of scope will make the constructor or the destructor of the class or the object it is pointing to work. That is the main principle behind smart pointers. We used a unique point. Now, how to use various of them, various pointers. One of them is the unique pointer, where if we want to just have access to only a single, have a single pointer, have access to a resource, like own it and change it and everything, then we use unique pointers. So in cases where you do not want many pointers pointing to the same one, it helps in keeping track of who owns what actually, because if all of them are unique pointers, you know that all of them point to the same, sorry, all of them point to some resources uniquely. Okay. in case there are cases, as we saw here, there are cases if you want to have many pointers pointing to the same resource, there might be cases you want this, and still you do not want to worry about keeping track of where all if all my pointers have gone destroyed, or I have to worry about deleting them. That also is not an issue with smart point if you use smart pointers like shared pointer, because as soon as here the auto scope happens for all the defined pointers q, p, and whatever I did, so all of them get destroyed. So very simply, you can have very nice memory management if you use smart pointers, either the unique pointer or the shared pointer, or like temporarily have ownership with weak pointers. Okay, so that will be all. With this, I'll end whatever I wanted to cover today. So if you have any questions, you can feel free to ask, or else we can end the class. Yeah. I hope you guys had fun learning all the topics. So this will be the 12th TS week for the TS sessions. This essentially covers all the modules that are there in the NPTEL course. Yeah, there will be an extra TS session next week. I've requested NPTEL to uh, give a slot. I don't know if NPTEL has shared that with you guys, but if you have any questions, I'll join the next week also. That will be the last class. And yeah, hope you guys had fun learning this uh, course. Yeah.
So what do you mean by out of scope?
Okay. So if you look at this example, right? So anything that is defined under curly braces is in scope. What I mean is,
Okay.
so let's say SP is something like there's some variable with some auto, like whatever is data type is. So SP was not ever defined anywhere else. It's just defined under this curly braces. Okay. So I define SP, and as soon as this uh, curly braces ends, the lifetime of SP ends. So that's what we mean by out of scope. So a scope is anything which is within two curly braces. Even main function also, or whatever body you see for a function. So this void function, right? So its body, this is the scope of this function. This is the scope of the main function. This is just an empty scope. You can have scopes without any, like it need not be of part of a function itself. It can just be an empty scope. Yeah. So when I say out of scope, any variable which is inside a scope gets out of scope when the scope itself ends. That's essentially the idea. Now, this going out of scope is what makes your the RRI or RIID actually work. So when something goes out of scope, it's destructive of let's say some kind of if I have a if I have a class and an object, so when it's a feature of C++ itself, when that uh, object gets out of scope, its destructor gets called. When the destructor of a smart pointer gets called, whatever resource it was acquiring, its destructor will get called. Okay, that's automatic. And then your resource gets deallocated. This is a very nice thing about C++. Like if you're using smart pointers, memory management becomes very easy. And yeah, essentially it brings C++ even closer to Python in the sense of you don't have to worry about memory. So that's the thing. I hope this is part is clear.
Yes, sir, it's clear. So otherwise, when we were using normal pointers, we had to delete them
Yes,
after we had finished using them.
correct, correct. So whenever you use new or malloc or something, malloc or all others are from C. So if you use the new operator, then you have to use delete operator. This is the C++ way. Yeah,
Okay.
yeah.
And sir, can you please explain me how are you writing this standard double colon make shared int?
Okay. Oh, that is just the syntax. So think of it this way. The syntax for making a unique pointer or a shared pointer, anything, is this. So standard is the namespace. Okay. Inside that, I have something called a unique pointer. Okay. Now P is the pointer. Okay. But for now, this unique pointer is itself a class, but a templatized class. Okay. So templates are um, written inside this angular brackets. And what you pass is the class that you want to point it to. So you want to create a smart pointer out of some class. So let's say foo is my class, second class. Like unique pointer is definitely a class, but foo is a class for which I want to allocate some resource and have a pointer pointing to that class. P is that pointer. Okay, so this is just a syntax for doing all that. Now you can do it two ways. The 14 way is have a equal to write standard colon colon make unique, also templatized class where you pass foo and then the no parameter needed. If it's required, then you can put it. Here it's not required. Or have the same everything and pass argument as, yeah, here you don't you can just pass new foo. So new will create a pointer to it will create an object, and whatever pointer to it, it will return and then pass it to P. So the constructor for P will take that new pointer and make a unique pointer, which is the P itself. It's just a syntax for it, similar to shared pointer in. Okay. Now here I passed some um, user-defined class like foo or something. You can actually pass inbuilt um, types. So integer, double, and all, absolutely valid. So instead of unique pointer, here it will be shared pointer, shared underscore pointer. And here P is a shared pointer. And similar to previous, I have a function called, I have a class called make it, like very similar to make unique. I have a class called make shared. I pass the same integer because I want to make a integer make, right? And give a bracket. So this will create a integer allocation. Okay, this line, this whole select. This whole line will create a integer allocation, and the pointer that is pointing to it will be stored inside P. This whole syntax makes sure that you're making a unique, not a unique. You are making a smart shared pointer P. And in this line, we are just dereferencing P to store value 3. That's it. It's just a syntax if you think about it.
Okay, so basically we are creating an object of integer and we are pointing our pointer towards that object.
Yes, object, yes. And that pointer just happens to be not just a simple pointer, it is a special pointer. It is a shared pointer here. And
Okay,
in this case, it is a unique pointer. Yes.
and sir, can you please move to the fifth one, the smart pointers 5?
Okay.
Um, no, sir, the fourth one.
Okay.
Sir, here you have written p dot reset new comma new int 11. So
Yeah.
is int to be written compulsory?
Um, it's not needed, but let's say because I've defined my pointer to take integer, like integer pointers, here I'm making sure that 11 is treated as an integer, not long integer or something else. It's just a I'm being more explicit here. That's all.
Okay, sir. Okay. Sir, so p dot use count means that the object to which the smart pointer p is pointing to is
Yes,
shared by how many pointers?
correct. How many shared pointers? You can
Okay,
have you can have raw pointers pointing to it, but shared pointer will not have any knowledge of that.
okay, sir. Okay,
Yeah. And let's say you try to make a unique pointer out of it, that is no, that is not allowed because there are already shared pointers pointing to it. And smart pointer wise, only a single for let's say it's a unique pointer, only a single pointer smart pointer can point to it. So we can't make smart in this case at least for whatever resource three is has like whatever three sets, we can't make unique pointer here. We
okay,
can
sir.
we can if we like if we reset p, let's say we reset q also, then we can make a we can take the raw pointer from it and then make uh, a unique pointer out of it. Yeah.
Okay, sir. Sir, in this example, when you did p dot reset, to which object p was pointing then afterwards?
Oh, it's null. If you give nothing, it's just an empty pointer. It's not pointing to anything.
Okay, sir. So, then if we had written the same statement p dot use count, then it would have showed un.
It should actually show you zero because it's not actually pointing to anything. We can put something, maybe I'll put it at 2.9. Yeah, points to, it shows zero because currently it's not pointing to anything, as in nothing is being pointed to. So if I have a
Okay,
if I think of it like a resource, which is how many pointers are pointing to, let's say by p, which is zero because there is no object at all. So yeah,
okay, okay, sir.
yeah, that's a good question. Yeah. So actually, thing is, with a lot of these things, you can just try printing stuff and working like to understand how okay how this function of this use count or any other property, how does that work? You can just try playing around. A lot of these things become clear when you actually uh, try out the code itself. Yeah, that's yeah.
Okay, okay, sir.
Maybe just like, see. can add few lines here also. So let's say I just want to print P. Yeah, P. Then maybe here. So yeah, it prints 11 because that's what it is pointing to. So dereferencing it prints 11, and null pointer is like it's not actually pointing to anything. So if I try to dereference, it just throws a fault. Yeah. That's- Okay, great. I guess we can end the class here. Again, my recommendation will be to more like better understand all these concepts in program like modern C++. You just have to play around. Take the whatever function standard make unique lambda expressions, whatever. Play around with different examples and then try it out. That's how you'll understand these examples better. All these codes and everything I'll upload in the Google Drive. So you probably should have access to that. If not, mail NPTEL. And lectures also I'll upload. I have been uploading for all of them. So this lecture will also I'll upload. And yeah, I guess that's it. If possible, I'll have the. I've asked NPTEL, but let's see what they say. If they have replied to you guys to have, then we'll have an extra TA session, which will be the last TA session. Okay. With this, we can end the class today. Thank you.
Thank you, sir.